In my talk, I wanted to there's correct. In my talk, I wanted to tell you about our theoretical study where we explored the possibility of visualizing isolating layer, and when the voltage bias exceeds twice the superconducting gap, then the quasi-particles tunnel between the superconductors, and of course the heterostructure, so approximatizing two-dimensional electron gap perpendicular magnetic field, they exhibit Fraunhofer oscillations of the critical current. So the SNS junctions are a bit different as compared to ordinary SIS junctions, because now between the superconductors we have a piece of normal material, and of course there are available states for electrons. Now the the transfer of Cooper pairs between the superconductors happens by pairs of electrons and holes that bounce between the superconducting electrodes, creating so-called undrift bound states. The energy of those undrift bound states is controlled by the phase difference between the superconductors. Understand what happens. We are interested in the critical current, which is obtained as a maximal supercurrent that is carried through the junction, and the supercurrent comes from the supercurrent distribution integrated over the junction cross section. The supercurrent has some initial distribution, which we take as a constant across the junction, and the phase-dependent term, that distribution in the junction. Let us focus on a cross-section through the junction. So if we position ourselves in the first minimum of the Fraunhofer pattern, we see that the supercurrent distribution has this oscillation. So if we modulate the phase difference between the superconductor, maximal critical current. Also, it is important to notice that in this situation, phase difference value that gives us the maximal critical current, and this is exactly the one that I'm showing on the screen right now, where there are two positive lobes of the supercurrent. We learned that in SNS junctions, the current in the magnetic field form this kind of streams of positive and negative supercurrent, and we asked ourselves if there is a way that one can actually see this supercurrent distribution in an experiment. And we want to use for that a technique which is called scanning gate microscopy. This is a well-known technique in semiconductor science, and it works as follows. When there is a two-dimensional electron gas in a heterostructure, we can measure the conductance of this device. Let's say we have a QPC in the middle, but at the same time, we scan above the surface of the system with a atomic force microscope tip. Obviously, this tip would, if it's negatively charged, it would create a repelling potential for electrons that reside in two-dimensional electron gas, and by that